So let's talk about the carbon cycle. First, my question to you, why is carbon important? I'll give you a second to think about that. Did you come up with anything why carbon is important? Well, the biggest thing, think about living things. All living things that we know of here on Earth are carbon-based organisms. So obviously carbon plays a huge role in life on Earth because it is what is going to form all of our significant organic compounds. Organic means there's carbon, usually more than one molecule or atom of carbon, usually two or more, attached to at least 4 hydrogens. And so carbon is in all of our significant macromolecules. And that's the biggest reason why carbon is important to living things. So some of our large reservoirs of carbon, remember a reservoir is a long-term storage location. The oceans and the oceans including the water itself, because carbon dioxide can mix with water to form carbonic acid, and that can stay as an acid in the water. Also, the sediments, the silt and the sand at the bottom of the ocean can trap a lot of that carbon and sequester it away for thousands of years. And the word sequester is one of my favorite words. I love it when kids use the word sequester or sequestration in their FRQs. And when you sequester something, you're keeping it aside. You're making it unavailable to use by anyone else. And so the sediments at the bottom of the ocean, which are generally not being stirred up or anything like that, they're going to be a great place to sequester or keep the carbon for a long period of time. Speaking of long periods of time, sedimentary rocks are also a great example of a large reservoir for carbon. And then the atmosphere, this carbon dioxide in the atmosphere is a huge source of carbon. So when we talk about the carbon cycle itself, there's two processes that we generally refer to that go together, photosynthesis as well as cellular respiration. I talked about those in one of the earlier videos from the chapter. If you're not familiar with the process of photosynthesis or cellular respiration, I suggest that you become familiar with them. But the products of photosynthesis become the reactants for cellular respiration and vice versa. So they go hand in hand, and the carbon cycle actually kind of goes together along with the oxygen cycle. We don't really get into the oxygen cycle, but they kind of, similar processes because there's oxygen attached to the carbon and carbon dioxide and glucose and all that good stuff. So the two main processes that were part of the carbon cycle, photosynthesis as well as cellular respiration. And these are the natural processes. Of course, when humans come into play, that's when we start messing things up. And we're taking that sequestered carbon and then burning it through the process of combustion. But these are your natural processes without any human interference. When humans interfere, some of the other processes that play a role in the carbon cycle, decomposition, that's not really human influenced, but decomposition as bacteria are eating away at dead organisms and releasing the carbon that was stored in their bodies, putting that carbon back into the ecosystem. Combustion, notice I have the little asterisk there because that's your true big human source. Combustion or the burning of things like fossil fuels, coal and oil and natural gas that would normally be sequestered and buried underground for forever almost. If there are no humans on Earth, there would be no combustion. We wouldn't have burning of fossil fuels, and that carbon would stay trapped underground and wouldn't be emitted into the atmosphere, and it wouldn't be acting as a greenhouse gas, and the Earth's temperature wouldn't be getting warmer. So this combustion obviously is a huge, huge problem when we're talking about greenhouse gases and the process of Earth heating up. Weathering of rocks, as the rocks are being broken down either through biological or chemical or physical weathering, can release some of that carbon, and the eruption of volcanoes as well. So as carbon is moving, as carbon is moving through the cycle, it is going to be affected by the amount of primary productivity, so the amount of plants that are there, and the amount of plants is going to be affected by the amount of sunlight and the amount of rainfall, therefore affecting the photosynthetic rate, which is what primary productivity is all about, and also decomposition rates. I mentioned in another video that decomposition is going to increase when you've got warmer temperatures and more precipitation. So in places like tropical rainforests, where there's a plethora of plant life and it's nice and warm and it's constantly raining, then you've got a high rate of primary productivity, you've got a high rate of decomposition, so that carbon is moving through the ecosystem relatively quickly. It's going from the soil and getting sucked right up into a tree, and the tree or whatever plant is producing leaves and fruits, and maybe an animal comes by and eats the fruits and then incorporates carbon into its body, and maybe the animal defecates somewhere, and that fecal matter is then broken down by decomposing bacteria, and that carbon gets put back onto the soil, and then the plants can take it up again. And so in certain areas, like a tropical rainforest, for example, carbon cycling happens really rapidly, whereas in other locations, the carbon cycling happens a lot more slowly because it's cooler and there's perhaps not as much precipitation. So the cycling is going to be contingent upon the temperature and precipitation rate. I hope that makes sense to you. So as I mentioned before with combustion and my little asterisk there, we humans are interfering with the carbon cycle in a multitude of ways, and this is just a few examples, by clearing trees or deforestation, however you want to phrase it. When we are removing the trees, we're removing a really important source that is taking in carbon dioxide. Your trees are able to take about 15% of the carbon dioxide out of the atmosphere. And so as we get rid of plant life to make way for, parking lots and high schools built on the Everglades, as we are getting rid of the plant life, that means that we are decreasing the amount of, or we're getting rid of the trees, which in turn is going to affect the amount of carbon dioxide in the atmosphere. So that's having a huge influence on the carbon cycle. And that's why you see a lot of companies nowadays that say, like, for every one tree they cut down, they plant 2 more, because they're trying to get things back in balance. The burning of fossil fuels, which I've already mentioned, aka combustion. So let's say we're talking about coal. So we mine for coal, we take it out of the earth, and then we burn it to produce electricity. And burning is known as combustion. And so as we burn the coal for electricity, carbon dioxide is produced as a byproduct. That carbon dioxide goes up into the atmosphere, and it stays in the lower portion of the atmosphere, the troposphere, that's closest to the surface of the earth. And it acts like a blanket. It traps heat that's trying to be radiated back out into outer space, and traps that heat near Earth's surface, making it warmer and warmer. And that's part of the greenhouse effect. Yes, there's naturally occurring carbon dioxide in the atmosphere, but it's when we humans start burning coal and petroleum, aka oil, and releasing that carbon that would normally be sequestered and kept away, we put that into the atmosphere, and now we're increasing the greenhouse gases, and they're trapping even more heat next to Earth's surface. That's what the human-induced greenhouse effect is all about. I will talk more about that later on in the year, but I just wanted to give you an idea. I want to impress upon you this importance of taking carbon that would normally be sequestered away and releasing that into the atmosphere, exacerbating the greenhouse effect. So what we're going to be looking at in one of the labs that we do is we're going to be collecting carbon dioxide from 3 different sources, and getting a rough idea of the concentration of carbon dioxide from vehicle exhaust, from your respiration, you're going to breathe into something, and also from the atmosphere. We're going to see which one contains a higher concentration of carbon dioxide, and do some other stuff too. Another lab that we'll be doing later on is looking at the effect of carbon and the oceans. Now, carbon dioxide in the atmosphere is going to also mix with water on the surface of the ocean. Carbon dioxide, CO2 plus H2O, forms an acid, H2CO3. It's called carbonic acid. It's a relatively weak acid. It's the same acid that you have in your soda pop. So it's relatively weak. It's obviously not going to corrode your skin or anything, but if you drink soda on a daily basis, it's not so great for your teeth. So this carbonic acid that is being formed naturally in the oceans, we can't stop water from combining with carbon dioxide, so this is a process that occurs, under normal circumstances, but now that we're putting more carbon dioxide into the atmosphere, there's even more of this happening. So we've got more and more carbonic acid forming in ocean water, and you might have heard about ocean acidification. This is where the pH of the ocean is starting to change slightly. It's not a significant change. Remember, the pH scale is a logarithmic scale, so we're not changing from like a pH of 8.3, which is normal ocean water, to like a 7.3, but it is going down a little bit. And this is really significant for organisms that have shells or exoskeletons made of things like calcium carbonate, like coral reefs. And so you always hear about ocean acidification and coral reefs. The reef's skeleton, the limestone skeleton of a piece of coral, is starting to be eroded away by the change in the acidity or the change in pH of the ocean. And so this is a huge, huge problem, which we'll talk more about in Chapter 8 when we focus on aquatic systems. So that H2CO3, the carbonic acid, can also dissociate. That's what your little two-sided arrow is looking at. And so it can dissociate into bicarbonate ions. Bicarbonate, not so bad for the ecosystem, but the fact that we are kind of loading the ecosystem with carbonic acid, there's less dissociation into those bicarbonate ions. Bicarbonate can be used by many organisms, but we're going to focus on the carbonic acid in a lab that we're doing later on. So what we humans are doing to the carbon cycle, you can see in this diagram here. And again, you have this picture in your textbook. I don't know what page it's on. The red arrows indicate natural pathways. The blue arrows indicate, the blue arrows are natural pathways. The red arrows are human influence. And you can see all of the arrows leading to carbon dioxide in the atmosphere. So those are all a bunch of processes, both natural and human impacted, that are adding to the CO2 in the atmosphere. And notice that the burning of fossil fuels or combustion over here on the right has a very large arrow because it's contributing a lot to the amount of CO2 in the atmosphere. So make sure you go ahead and spend some time looking at this diagram. And if you're not sure about something, of course, ask me. And this is just a simple little graph. Obviously, it's not really a very technical graph, but it is showing the increase in atmospheric CO2 from the 1960s to 2009, which is when your textbook is from. So you can see there's been a general increase. And at this point in time in 2017, we are above the 400 part per million mark. That is hugely significant. That is a lot of carbon dioxide. We haven't had these concentrations in such a short amount of time ever happen. Excuse me. And that's kind of what is the scary thing, is that CO2 concentrations have increased in such a short amount of time since we humans have figured out how to burn fossil fuels. That's kind of significant. And I think that's what I have there for the carbon cycle. We'll talk more about the nitrogen cycle later. If you have any questions regarding the carbon cycle or anything else from Chapter 3, please let me know. Bye!